Hello, everyone. So my name is Emily Grams. I am a process analytics engineer at Owens Corning. I've been with the company since the beginning of 2017. Started out as a line engineer and then a shift supervisor. Then I started into an R&D role with the goal of pairing analytics technologies with our manufacturing environment. And I'm here to share with you today a digital twin that we used in a few of our manufacturing plants, and an example of how we applied it. So Owens Corning is a global enterprise with sales of 7.2 billion in 2019. We have roughly 18,000 employees and a presence in 33 countries globally. We deliver a variety of insulation and roofing products for commercial and industrial purposes, as well as residential purposes. We also produce fiberglass composites that are used in everything from cars and bridges to wind energy and personal electronics. So for our digital twin case study, our initial rollout was in 2 of our residential roofing plants. Roofing alone was a $2.6 billion business in 2019. Our shingles are comprised of a glass fiber composite that's coated with an asphalt filler mixture and mineral granules. The plant in this particular rollout produces architectural shingles and a 3-tab residential shingle. Getting into the digital twin, we first investigated potential process twins when we saw a need for our plants and engineering teams to get fast access to large amounts of process and quality data for analysis. We selected a web-based process analytics and management app, which utilizes a structured database. The software we selected served 2 main functions for our operations, so a back-end database with structured process data, and then a front-end analytics package that gave us an ability to identify optimal performance from our historical data and then tracking capabilities to maintain that performance. So the first portion of the digital twin software that I want to touch on is the back-end data structuring process that we went through. So we feed relevant process data from multiple sources, for instance, data from our process historian, and we even feed quality data and COA data in some of our plants. And then what that process model does is it takes that data that we feed it, it lags it all to a common time step using calculated vessel residence times, and then that changes given our process inputs. So what we'll do is we'll feed it level changes, flows, vessel dimensions, and then the process model is constantly updating the lag between process equipment. So if we have a slow time or a downtime, the model will adjust to fit the changing process context. So this will allow us to correlate between process changes regardless of where our sensor measurements are being taken. So once the process data is structured in your database, you can actually begin establishing relationships between process variables and test the effects of input variables on output variables. So within our selected software, we were actually able to correlate a KPI's good performance that's user-defined by the engineers in the plant, and then correlate that with multiple input variables at one time using a cross-rank system. So to obtain a cross rank, the data is placed into discrete operational windows. Then within each window, the software identifies exactly how many points are in that window, and then what percentage of those points led to good or bad performance of our output variable. Input variables that have more points in areas of extremely high or low performance earn a higher cross rank and are more correlated. This method was preferred because it actually allowed us to address some of the challenges you face with trying to find correlations in process data. So non-normality, discrete values, and outliers. The analysis tool is actually able to handle all of those odd things that you'll find in process data. In addition, we're actually able to record these relationships and make set point adjustments or pairs based on how a particular set of inputs have been impacting the output performance of the software. The case study that I wanted to share with you guys. So in one of our residential roofing plants, we worked with the tech leader and we had identified a significant issue within their filler system. So within our process, we mix asphalt with a filler material that's preheated. The plant's technical lead had noticed that in the process, it was not able to maintain optimal temperature for production despite no apparent change to our settings or startup procedures. What we needed to understand was what had drifted in the coding process while considering any process lags in that correlation. So upon running an analysis, we had noticed that the filler temperature was significantly limiting the filled coating temperature. Then the tech leader actually went back and looked into what led to that lower filler temperature and identified periods of runtime where we were getting little to no heat exchanger fluid flow to their filler heater. Now, this was an issue that the tech leader had mentioned would normally have taken weeks to identify and traditionally would not have been noticed by the plant personnel until it was causing significant run issues for their plant. So to resolve this issue, we repaired the mechanical failure that resulted in the upset condition. And then in addition to the repair, we wanted to track these variables to prevent similar issues in the future and further optimize the process if possible. So what we ended up doing was we took those identified ideal ranges for the filler system variables using the analysis module. And now we are monitoring how well we are maintaining these set points, and we're actually able to see the real-time impact on our key output variable of coating mix temperature. So this is different than traditional SPC because we're not just trying to keep track of individual variables' performance within a particular range. We're actually looking to control particular inputs and see how they affect an output, which is the main benefit of using a digital twin to model your process. So outcomes. So what were the main benefits of utilizing a digital twin within the manufacturing space? So with this particular case study, we were actually trying to achieve productivity. We were actually able to achieve a significant materials cost savings. Some additional benefits that we got out of the tool were we found engineers were spending less time actually structuring data for lag times on their own. Normally, an engineer is interested in looking at it. If they're interested in looking at an event and it took place around a slow time, the engineers would have to manually take that into account. But with the process twin, this is already accounted for us. It also increased visibility to what was shifting over time in our processes, and it also helps us capture some of that knowledge from senior engineering leadership. So some of those core fundamental process relationships that we'd like to keep track of, we're actually able to record that and track that in the tool. We also learned a lot of lessons throughout this whole process. So although digital twins are a technology that can be useful in understanding your process, without data gaps being closed and proper maintenance procedures in place, process modeling is limited or not possible at all. You won't be able to calculate residence times if a data feed is unreliable or non-existent. In addition, any relationships that your engineers know exist on a fundamental level will be obfuscated if your data feed isn't kept in optimal shape. We also saw how important it is for facilities to actually have resources to shift from that reaction mindset to a predictive one. It's really hard to think about and optimize for the future if you're constantly thinking about the next fire to put out. So helping plants with this digital transition is going to be critical for any technology that you implement in the future. But I'd like to thank everyone for your time today. Please let me know if you have any questions in the Q&A sessions later.